Yes. So thank you very much for having me and for giving me the opportunity to present some of the developments and some of the results from IQM quantum computers. Actually also thank you very much for the very nice theory introduction. So that helps me a lot, so I can really dive right into the hardware section. Okay. So I'm working for IQM Quantum Computers, which is a Finnish startup with sort of a second largest place in Germany, in Munich. I'm usually based there. And what we do, we actually build quantum computers. Of course, like every company, we have sort of a very nice punchline, but actually our true aim, if we really go to the heart of it, is to build the quantum computers which would be needed for these applications. Now, this is a very hard task. So it takes quite a significant amount of resources, and like many others, we have grown to now almost 300 employees. So this numbers is maybe a little bit outdated, but it is still all really in the deep tech regime. So we have a very high proportion of highly skilled PhDs with a very specific quantum education. Of course, you need some funding. Like everyone, we are also always looking for some funding, and we have some funding. And actually, we have built in our labs more than 30 of such R&D quantum systems, and we have already delivered some of them to customers. And this is maybe one of our specifics, that we really aim to provide these systems to customers already now, where these systems, while they're still small, we have heard, are mostly used for R&D. So one can have them on-premise and really play with them and own them. Yeah. Then this is actually particularly interesting for HPC centers, maybe not for the very commercial ones in the beginning, but for those who are more research-oriented, like the VTT in Finland or the Leibniz Supercomputing Center in Munich, but also some of the Euro-HPC, like the participants, like the IT4I in Ostrava in the Czech Republic, and some others. We now have quantum computers of up to 50 qubits, and we are planning to have a 150 qubit variant soon, meaning maybe sometime next year. Okay. Now, it has been outlined already that the path to quantum computing is a tough one. And this actually becomes quantified in the roadmaps of the hardware manufacturers. You may follow some of these roadmaps, and you may have seen our roadmap. And it's a bit of a busy slide, but actually you don't need to dive into all the details to get the take-home messages of it. The first is, if you look at the topmost line, and if you look at the time horizon, you can already see that the challenges are such that a truly commercially useful device, in the sense, that it's not bought for educational purposes, but that it would be bought by a company like these kind of devices to produce additional value elsewhere. This is still a little bit further out in the future, unless, of course, a dramatic breakthrough or development happens, which many have already happened in the last years, and which one can never exclude. Yeah? So these are always snapshots given on today's technology and today's understanding. We predict that this would be maybe around 10 years out in the future, 5 to 10 years. Then the second thing you can see is that it's kind of a holistic undertaking. Even if you're building hardware, you kind of need to have the applications in view and need to have some understanding. So you need to have some understanding about what's going on in simulation, in optimization, in machine learning. These have already been key potential applications mentioned in the previous talk. But then you also need a software platform to kind of link these algorithms to your hardware and also to control your hardware. So these are very classical systems which you need actually to support your quantum computer and to actually operate it. And then, of course, you need to think about the heart, which is the quantum processing unit. Then you see here in this slide that with maybe the current technology and even if we like predict some improvements in the physical gate fidelities, it will take the error-corrected path, because actually really improving the gate fidelity very much is going to be very, very hard in most people's judgment. So it will take on the order of 1 million physical qubit devices to get there. Yeah, this is where we need to go. And then I've shown you here the red contour. This highlights again the devices where we are today and on which I can talk something. This is already quite some achievement actually to get this, and it has mostly already taken commercial deep tech research to get there. So this is already very hard to achieve in academia and academic groups. Yeah? But I will focus on those which are sort of on the few to say 50 qubit level and outline some progress here. But always keep in mind that everything we do with having this scalability to this really 100,000 and millions of qubit systems in mind. Okay. Now, how to make these accessible? I've already shown that some of our customers are these research-oriented R&D oriented HPC centers, which are usually connected to some universities or groups of universities, and they of course make these systems then available to these university groups, and they see this as part of their research about the future of computing. They come from HPC computing, of course, and they see quantum computing as a potential either addition or part of the future of HPC computing. And the other option is you can, of course, try to have some cloud access, and there also, like many companies offer this, and also IQM, so I can just encourage everyone to really use this kind of R&D access and to start playing with these systems today, because there are a lot of things to be learned, and the quantum computing companies, even if you take all of them, all the IBMs and Googles and IQMs and Quantinums and you name them, yeah, then we don't have nearly enough people to do all this wide research which the whole quantum community can still do. So you see in the roadmap that we are still in kind of early stages. So we really need you, and this is one way how you can somewhat easily participate. And that's also typically the motivation to provide this cloud access. Okay. Now, let me get to some actual devices. And one of the devices we have launched about a year ago is our 20-qubit QPU, and it is based, as you can see here in the center, on a square grid lattice with some nearest neighbor connectivity. Every qubit, which is in the center of the lattice, of course, has 4 nearest neighbors. This makes sort of this local connectivity, and next to the blue dots, which are the qubits, you see the green dots, and these are the so-called tunable couplers. And this is a bit of a technicality, but these are additional quantum circuits which we actually need very much to operate the qubits in high quality. Yeah? Because it's a challenge if the qubits are just coupled to each other, that when they make operations, they should do fast operations. So they need to be coupled very strongly, very, very tightly to each other. However, when we do operations elsewhere, we would like them to be well decoupled. So if we have only a fixed coupling, we would always have to take a compromise between these two worlds, and that's difficult. And that's why we have the tunable couplers, and we see also others to converge to this kind of technology or to use it. And this is really important to achieve high fidelities on the order of these 2 to, or say 3 nines, which were demanded to go towards error correction. Yeah? And then we can look at this device, and you can see that at the 2-qubit fidelity for this kind of device, we are at kind of 2.5 nines. This is already pretty good. In practice, actually, this does not really, this is all formally above threshold, but then when you really run some error correction algorithms, there are a lot of details. You have to worry about crosstalk. Yeah, what is here is when the gates are run by themselves. So it's still slightly above the threshold for this device, but you can already really explore quantum error correction with this kind of device. Like going away from error correction, at the very basic idea, there are some typical key numbers what makes these devices perform better or worse. And one of them is, of course, the gate fidelity. You can see the 2-qubit gate fidelity. You can see the single-qubit gate fidelity, which is fortunately a bit higher than the 2-qubit gate fidelity, because that's also typically what we would like for error correction. But then we need to ask, what can this already do, if we do some IND? And for this, you ask the quantum physics question, you need the property of entanglement. If you really want quantum effects between all those qubits, you need to entangle all of them. And the simplest measure you can have for this is the so-called Greenberg-Horn-Zeilinger, so a GHZ state. And you can see that here the parameters are already good enough to entangle all of them. And then you have some quantum volume, which says like sort of a subset of 5 qubits can satisfy this very demanding quantum volume test. Then you need to worry about real-life execution speed, which is typically the strength of the superconducting circuits. And then there are some Q-cat. This is some optimization actually based on a Q-score. I'm sorry, not Q-cat, Q-score. This is based on a max-cat algorithm on a certain set of graphs. And here you can, for this particular set of graphs, you can do something useful with up to 15 qubits of this QPU. So this gives you an idea. Then we are already scaling this QPU. And our largest system available at these times is a 54-qubit system. One of these has been delivered to VTT already. In our cloud, a system will come online soon, and also very soon later this year, one of these systems will be delivered in the framework of the Euro-HPC program to the Leibniz Supercomputing Center in Munich. And here I show you some data of an internal test device. And you see again that in the single qubit, I'm sorry, it's a bit technical. I think it's good enough for most to look at the numbers in these cumulative distribution plots. Everything else is for the experts. You're welcome to ask me questions on these details after the session. But you see that this has at least reaches similar properties as the 20-qubit system. Actually, if you look at the center trace, the median 2-qubit gate fidelity is here 99.1% roughly, so it's slightly worse, but it's not that much worse. And that's really one of the challenges of scaling, because as you scale, the crosstalk increases and the control challenges become more drastic, the packaging challenge, all the non-quantum technical challenges become more and more difficult as you scale. And it's really important when we say error correction means that you reach a certain fidelity and then you increase the qubit number, that you can increase the qubit number without sacrificing this fidelity. That's the actual challenge in scaling these days. And that works on this level already quite nicely. When we scale, actually calibrating of the quantum computers is a very important problem. It may sound a bit boring, but actually it's the key. So the problem if you have an academic quantum in some university lab is that typically you need the PhD student or the postdoc who built this up if you ever want to do something on it. Because, I mean, to get it into a state where you can do fancy things with it, you need a lot of expertise. And this process, this calibration process, is now being tackled and automatized. And that's actually a lot of research and development on our side is going into that. And one of the important things is that if we scale the systems further, we need to calibrate not slower and slower. That would be very bad if the calibration time would scale with the number of qubits. Yeah? So, so we are developing parallel calibration schemes, and this means we are dividing actually all the qubits into certain subgroups in a way that we can tune them up simultaneously without hurting nearby operations and qubit tune-up so much. So this is one of the points. And the other point is that we have quite a few parameters, right? And I'm highlighting here only 3 of them, which is the single qubit gate fidelity, the 2-qubit gate fidelity, and the readout fidelity. And all of them need to be as good as possible, but like if you have a lot of these qubits, I mean, you can have a lot of trade-offs between them. So you need kind of one number. You need to find a way for a scalable calibration to define one target how you want to calibrate your quantum computer. And this we do with this, what we call an error score, where we sort of give these gate fidelities a weighting factor based on the typical prevalence of these errors. And these weighting factors is roughly 5, actually, here, where sort of the lowest fidelities are allowed for the readout and the highest are demanded for the single qubit gate. And with this, you can then arrive at these cumulative distribution diagrams, and you see here on the right that you have arrived in an automated calibration at certain single, 2-qubit, and readout fidelity values, which sort of are roughly scaled with these factors. But if you do the math, actually you see that these are not exactly these factors, so these are only the weighting for the optimization, but of course we have physical mechanisms which still force a certain error not to go beyond a bound. Yeah, so, but these help us to find the best possible calibration state. Okay. Now, next, when we want to scale to these to large qubit numbers, we really need to work on reducing the qubit numbers. And it was already shown, actually, some papers by our competitors, and we are also looking into this direction. And but this means that you really need to develop novel technology. And in our case, we are looking at what we call the star architecture, which is still in a very basic state, but which we hope explores sort of an orthogonal paradigm to our crystal, so to our square grid lattice QPUs. And here we have kind of a central hub, which for some technical reasons is a resonator, and we connect the qubits in a star geometry around this. And this means this explores, of course, this is still a very basic device, yeah? But this explores long-range and high connectivity topology, similar to ion traps now also in superconducting QPUs. And it allows us to look at novel compute elements and to explore how this could offer advantages for error correction. And again, we need, of course, we don't want to deviate too far from our technology, so we use our standard tunable couplers, and that works fine. So for details, in the interest of time, I have to refer you to the papers quoted here, or again to the coffee break later. Maybe the main take-home message is that the gate fidelities we reach here are similar. They're still a bit lower, but we haven't optimized so much, but they're similar to the square grid, so this is very encouraging. Maybe in the interest of time, I jump this slide and I go to one of the mini applications of the many explorations we have looked at, this is one example of how to do a basic quantum error correction with this kind of QPU and to explore its properties. And this allows us actually to look at a so-called 4-to-2 color code where we can use 4 data qubits, D1 to D4, to encode two minimal logical qubits. So this is something that this allows you already then to do some logical operations and to really explore on a small scale quantum error correction. And in addition, we actually need these 2 ancilla qubits, X and Z, because of the Heisenberg uncertainty principle, you can never, in your error correction, measure your data qubits, because otherwise you would project them and destroy the quantum information. So you have always, the idea is always that you have these ancilla qubits in all error correction codes, and you will have these interact in a clever way with your data qubits to collect some information without destroying this information, and then to measure and project only these ancilla qubits. And of course, with larger systems, we could do more. Then you see this a little bit in this circuit, and maybe again, I don't want to go so much into the details, but there are like some outstanding features. First of all, we need to prepare a logical state, or I will comment on this in the next slide. And then you have this kind of musical repetition notation of a cycle. And this means that in error correction, you will have some basic stabilization cycle of your quantum information now in this large ensemble of qubits. So you encode a small amount of quantum information in a relatively large Hilbert space or large ensemble of physical qubits. So it is redundant in sort of an intuitive access. And what you do then is that you check regularly, has this information now changed or not by measuring these ancilla qubits, by sort of having these ancilla qubits interact with the data qubits. Those are the lines here between the red line, the resonator is kind of the hub for this interaction, and the data qubit lines. And then also, in each of these cycles, you measure your ancilla qubits, and then you can record what kind of error you've had, if you had errors, and if so, do some action like post-processing or correction or whatever is necessary. Yeah. So this can now be run on this kind of QPU. And I want to show you just a very simplistic example, which is this first one, this state preparation. And what you do there is you prepare a state in the physical qubits. But that doesn't mean it's there already in your logical qubits. So you need to run this kind of stabilizer cycle, this kind of error correction cycle once. And this first run will project your physical state, which you have implemented into your logical state. And that's the first thing you want to check. That's what I want to show you now. So we start from an initial state. Of course, we look at various physical initial states of these 4 data qubits. Yeah, but we look at up to 16 of them. But here, for simplicity, I focus only on one. And then you do one error correction cycle. And then this is already probabilistic effect. So then in 50% of the cases, you will have prepared your proper logical state. And in other 50%, you will not have prepared it in this kind of simplistic experiment. And then you run this error correction cycle, and you still have some errors. And then we can have a look and do a tomography and try to find out whether we really have produced this logical state. Now, this is already a bit of detail, and I'm not going to go into these details, but fundamentally there are techniques, and the technique is called classical shadow tomography. And what you do is actually you can measure the physical states of the data qubit, so that's fine, you destroy them now, but it's not for checking, it's only for checking, right? It's a test experiment, so we can destroy the state. After measuring these, then from these measurement results, with some appropriate math and formalism, you can actually find some information about the logical state you have encoded. And in this case, we have encoded this very simplistic logical state, which is just the logical 0-0 state. We have also looked in this paper cited here at other states, but I'm showing this very simplistic one, and just to show you that this can be encoded with a quite high fidelity. The price we pay in this experiment is that this is not, we are not below threshold, so this is not a truly error-corrected quantum computer in that sense. We pay the price of course, post-selecting a lot of data. We take a lot of runs, and we throw away those which have errors. So that's the simplest way of doing error correction. That's of course not scalable, but for a device like this is a very good approach to get some understanding about these mechanisms and how these things work. And this is like what you would expect. You would expect actually in this actually one column, and if you have a fancy quantum superposition state, you would actually expect in this diagram more of these bars to show up, and some of them at various places. This will tell you what kind of quantum properties your state has. Okay. Maybe as a very last statement, we have meanwhile upgraded our 6-qubit device in the cloud to a 16-qubit device, which actually reaches, I'm sorry, not a Q-score, but the Q-score is actually more like around 10. But it reaches actually an entangled, maximum entangled state of 14 qubits. So we can entangle 14 of these 16 qubits at this moment. So this is a larger device where more fancy of these novel error correction codes requiring these long-range connectivities can be explored, for example, but also other things. Yeah? And this is we invite all the academic community to explore this, because we have now also offered a pulse level access tool via the cloud interface. So you can really go and play on a relatively low level with these systems while still having some checks from our side that you don't have to work all in the fog, essentially. With this, I want to thank you for your attention. Maybe at the very last mention that actually a 24-qubit version of this device will be installed in Ostrava at ID4I also later this year as a framework of the Euro-HPC program. So this is another option if you're collaborating there to get your hands on such a device. And I think my time's up, and I'm happy to maybe take some questions.
Thank you, Frank, so much.